Download this code from codegive.com, link in the description below. Understanding Depthwise Separable Convolutional Neural Networks. Depthwise separable convolution is a type of convolutional operation that is designed to reduce the computational complexity of standard convolutional layers while maintaining performance. It is a key component of lightweight models like mobilenet, which are designed for mobile and edge devices where computational resources are limited. What is depthwise separable convolution? Depthwise separable convolution consists of two main operations. 1. Depthwise convolution. This applies a single filter to each input channel, or depth. For example, if you have an input with 3 channels, RGB, you will apply 3 different filters, one on each channel independently. 2. Pointwise convolution. This is a 1x1 convolution that combines the outputs of the depthwise convolution. It effectively mixes the features from all channels. The combination of these two types of convolutions allows for a significant reduction in the number of parameters and computations, making the model more efficient. Advantages of depthwise separable convolutions. Reduced parameters, significantly fewer parameters compared to standard convolutions. Faster computation, reduces the number of multiplications needed, leading to faster inference times. Maintains accuracy. With proper design, it can achieve performance comparable to standard convolutions. Code example using TensorFlow/Keras. Let's implement a simple neural network using depthwise separable convolutions in TensorFlow/Keras. We will build a model to classify images from the SFAR10 dataset. Step 1. Install required libraries. Make sure you have TensorFlow installed. Bash. Pip install TensorFlow. Step 2. Import libraries. Python. Import TensorFlow STF. From TensorFlow.keras import layers, models. From TensorFlow.keras.datasets import SFAR10. Import NumPy as NP. Step 3. Load and pre-process data. Python. Load SFAR10 dataset. X_train, Y_train, X_test, Y_test, equals SFAR10.load_data. Normalize pixel values to be between 0 and 1. X_train, X_test equals X_train.astype, float32. /255.0, X_test.astype, float32, /255.0. Convert labels to one-hot encoding. Y_train equals tf.keras.utils.to_categorical, Y_train, 10. Y_test equals tf.keras.utils.to_categorical, Y_test, 10. Step 4, build the depthwise separable convolutional model. Python. Def create_model. Model equals models.sequential. First depthwise separable block. Model.add, layers.input, shape equals 32, 32, 3, SFAR10 image shape. Model.add, layers.conv2d, 32, kernel_size equals 3, 3, padding equals same, activation equals relu, use_bias equals false. Model.add, layers.depthwise conv2d, kernel_size equals 3, 3, padding equals same, activation equals relu, use_bias equals false. Model.add, layers.conv2d, 32, kernel_size equals 1, 1, padding equals same, activation equals relu, use_bias equals false. Second depthwise separable block. Model.add, layers.conv2d, 64, kernel underscore size equals 3, 3, padding equals same, activation equals relu, use underscore bias equals false. Model.add, layers.depthwise conv2d, kernel underscore size equals 3, 3, padding equals same, activation equals relu, use underscore bias equals false. Model.add, layers.conv2d, 64, kernel underscore size equals 1, 1, padding equals same, activation equals relu, use underscore bias equals false. Global average pooling layer. Model.add, layers.global average pooling 2D. Fully connected layer. Model.add, layers.dense, 10, activation equals softmax. Return model. Create the model. Model equals create underscore model. Step 5, compile the model. Python. Model.compile, optimizer equals atom. Loss equals categorical underscore cross entropy. Metrics equals accuracy. Step 6, train the model. Python. Train the model. History equals model.fit, x underscore train, y underscore train, epochs equals 10, batch underscore size equals 64, validation underscore data equals x underscore test, y underscore test. Step 7, evaluate the model. Python. Evaluate the model on test data. Test underscore loss, test underscore accuracy equals model.evaluate, x underscore test, y underscore test. Print, f test accuracy, test underscore accuracy .4f. Conclusion. Depthwise separable convolutions are a powerful tool for building efficient neural networks, especially for mobile and edge devices. In this example, we built a simple convolutional neural network using depthwise separable convolutions to classify images from the SAFAR10 dataset. You can further experiment with varying the architecture and hyperparameters to see how it affects performance. This tutorial should give you a foundational understanding of depthwise separable convolutions and how to implement them in practice.